We're live.
Okay, my presentation is Boolean Algebra, so called because George Boole, back in 1854, came out with this book, Investigation of the Laws of Thought. This is why we have Boolean Algebra. And so, development of much of mathematics, went on during the 19th century that led to the or advances during the 20th century, led to the mathematics, which was the basis for technical advances during the 20th century. But now we also have, during the 19th century, was the development of an algebra of logic called Boolean Algebra, which deals with the type of algebra. Most algebra deals with complex or real numbers or something like this, but the algebra of that we're talking about deals with just two things. We can call it true, false. We can call it plus, minus. Whatever you choose to call it. It's usually represented with a 0 representing a false and a 1 representing a true. There are even other forms of variable logic, that I won't get into, in which they're kind of like probability almost, that represent 1 as absolute certainty and 0 as absolute denial, and everything else in between. So a continuum between 0 and 1. There is some logics that are based on that. But we're only going to do the bivariate true-false logic. That's what we're doing, and we go here. We talk about the basic operations of this logic. In regular arithmetic or algebra, you talk about multiplication, division, all that stuff that you're accustomed to talking about, but in this one there are only two basic operations: disjunction or conjunction. I'm going to call it conjunction, which is basically and disjunction, which is basically or. And symbols for conjunction can be anywhere from the dot, raised dot. I don't like particularly the raised dot because it resembles multiplication, just for the very fact that it resembles multiplication. But it is also, for some advantages, there may be some advantages to using the dot, but I prefer to use the upward pointing caret, just as for disjunction, I prefer to use, instead of the plus sign, I prefer to use the downward pointing caret. And you call something else, but that's what I call the upward.
The wedge?
Yeah, the wedge, something. And then there's another symbol, which is the negation, which you use a squiggly line rather than a minus. I even saw another symbol which was something like this. It
looks like an L, like a sideways L.
But I'll use the squiggle. My choices are these ones that I'll use today, but beware there are other choices, and it's a lot of this is called negation. And this is the not or not, sometimes called the complement. It is breaking it down very simply here, but we stand on the shoulders of giants. The Greeks enabled us to get to this point, enabled Boole to get to his point, so that he could break it down very simply mathematically. And then these are the basic operations. There are several derived operations, but they can be, like the name implies, they can actually be derived from other operations, or at least defined with truth tables. Well, before we get into that, though, we'll go ahead and define these ones. Conjunction is the case that now, since we have two variables, you know, A and B, we'll talk about A and B. We'll talk about, let's see, let's make a little truth table here. Let's go ahead and make a big truth table here. Do an A, run through all the possibilities of A and B, because since there are only two values for anything in this algebra, it's very simple having two variables that you could represent all the possible values of A and B, because there's only four of them. So this could be represented like 0, 0, 0, 1. This would be like 1, 0, or 1, 1. I believe that covers all the four possibilities. So that you could do that. And here is, I'm going to write here A and B. I'm going to write here column for A or B. And I'm going to write that in order for A and B to be true, both of these have to be true, which we're representing 1 equal true, so just for reference here. And so therefore we have 1 there and zeros everywhere else. And then with the A or B, either one of them can be a 1, and so that only if both of them are false, then is the thing false, and it's true otherwise. So that's the way OR is defined, as it makes sense naturally, you know. And then the negation, if we just say take the first two of these B values and say what what negation B is, and just go that far on the table. We say that not B is, you know, since the B is a 0 here, it'll be a 1 here. And since B is there, we can go there. And we can also note some tautologies. The tautology would be where the entire column is 1 or 0. If you found a column to be 0, then you could take the not of that column and it would become a tautology. So,
what's tautology again?
Tautology is something that is always true. I'm about to write something that is always true. We're going to write, say, B or not to be. I
like it.
And we have, anyway, B or not B. See, then we have, you know, one of them is true, so we have true. B or not B, one of them is true, so we have true. That is an example of a tautology. Is an expression that is always true.
Yeah.
Here's an expression that's always false. Well, I'll have to go to another page here, but here's an expression that's always false. I'll just get rid of one of these guys. So we just do this one here and only go around that far, because we're going to use B in that expression here. We're going to say B and not B. Well, we just use B and not B here. That's going to be, since both of them are not 1, it'd be a 0. one of them is 0, so it calls like a 0. So that's so. But guess what would be a tautology? What would be a tautology would be an expression like B and not B. Put that in parentheses, and not. That would be a tautology, if you can see where I'm going with this. So
not B and not B.
Accord,
B and not B. Yeah.
And so that's tautology.
So okay. Since the two in the parentheses are obviously contradictory, then putting a negative in front of it makes it always a tautology.
Right, because you're saying it's not.
Okay.
It's not contradictory.
Yeah.
Yes.
But, okay.
It's like a double negative type thing.
I just let
that.
Right. Which means, I mean, like, if you wanted to put flesh into it, you're saying like it's either raining or it's not raining. It's a tautology because it's always true. It's either always going to be raining or not raining. So it's like under any circumstances, it's always true.
Yeah. I'll just do another thing here, which means that there is a. I think you'll grant me that that B is. I'm going to use this symbol here to mean identically the same as or identically equal to, just like I did in algebra. And then this is to be identically equal to the negation of negation B. And I think you can see that. In other words, it's the double negation rule.
Not B. So
which makes it B.
Yeah, which makes it B. So these are interesting things to think about. You know, when you're so Boole had his hands full for a few minutes. You know.
Well, what's great is like, because people will try and present an argument to you, and it'll sound really complicated. But like, if you can listen to like the way they present it, if you can materialize it in a formula like that, you can realize that what they're saying is absolute nonsense.
You know, and I was just about to say that too, because this can get pretty complicated, but really it's easy.
Yeah,
you know what I mean?
A formula.
Yeah, it's like the lawyer who tries to fool the countryman, and he's really saying nothing. You know, if you can just realize that he's saying nothing, if you can put it into a syntactical form, it's just, you know, that's the whole point of law.
What exactly is this process called in algebra? What are we
Boolean.
The Boolean algebra?
Boolean algebra. This is this truth table is the easiest way to do, like up to 3 variables. Past 3 variables, you can just use simpler laws that were, you know, determined using the truth tables to figure out your way around. You know, like, you know, it's got. I'm gonna go represent this differently. Remember, like when you had the multiplication in arithmetic, if you talk about multiplication and you have a 0 and a 1 and a 0 and a 1, 0 times 0 is 1, 1 times 0 is a 0, and then a 0 and a 1. That looks a lot like and, doesn't it? That was the motivation behind using the dot for conjunction. And for addition, if you do addition modulus 2 here on the 0 ones, you have a 0 1 here, you have a 0 1 here, you have 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 1 is 1. 1 plus 1 is 2, but modulus 2, it goes back to 0. Actually, this gets back to a different kind of OR called the exclusive OR. But if you include the OR, yeah, it's a little bit, that one's not as much like the arithmetic, but like the plus, but it's got that one difference. But here's what the table looks like, obviously, for you know, because just representing it this way, operating disjunction, and you got a 0 and a 1, and a 0 and a 1. Of course, you've got 0 1s all the way, and that's the difference here. So, and then you got, there's no difference here, basically, because you put in the and as you can see, both of them have to be 1 to. So that's kind of how it looks like if you do operation tables, which is not quite like the truth tables, but it may be in another respect. You can sort of see how it works mathematically, and that way that conjunction is almost like multiplication. In fact, it basically is. And addition is like something. The addition is a derived. I mean, again, a derived. We get to talk about now derived operations, which we talk about material implication. If A, then B. This is what back the ancients, you know, used syllogism. You know, A, therefore B, that was your modus ponens. Then you got, but when you say this, the syllogism is like it. B, then C, then A, therefore A, C. So it's like that's a syllogism. But derived operations are this is called material implication is generally given a symbol that, and it's represented in between the two variables, the two logic variables, and or the quantities. And here's what the truth table looks like, represented as a operation table. If you were to say, I'm going to say A here and a B there, then B is 0 or 0 or 1, A is either 0 or 1. And so if 0, then B. Here's an important difference between two branches of thought on this. The false premise normally would consider by classical, you know, mathematics or the logic to be true, but kind of some people aren't happy with that, and I can see why. The relevance, you know, from relevance logic, you know, people have trouble with that, and so we'll put a slash question mark, you know, and then for this one, certainly we have, if A is so, then B is false. That's clearly a false, you know, then it or a 0, and we have true there, and we have so that's the disagreement between two schools of thought, as it were, on that. And then we have another one called exclusive OR, which is represented oftentimes by this plus sign, or XOR, or I might even represent it by, since we have the disjunction symbol, I might even put a circle around the disjunction symbol. I invented that one. But I'm sure there's been all sorts of stuff invented, because it sure appears like when you got 6 symbols, you know, representing the same thing. I got I get this impression of people working independently of each other, you know, not collaborating very well.
Right.
But, this is exclusive OR, which that table I go ahead and use a more conventional deal there. Plus with this goes that if you have A over here and B, let's say A exclusive OR B, then 0, 1, 0, 1. So you have, if they're the same, then the answer is 0 or false, and otherwise it's going to be true, because one of them will be true. And so that's the way that truth table ends up. Turns out there's another law, which is I mean, you know, if you want to consider equivalence as or equals as so sort of a logical operator, the test to whether something is equal or not. You have A and B. You have 0, 1, 0, 1. 0 is equal to 0, so that's a 1. 0 is not equal to 1, so that's a 0. 0 is not equal to 1, so that's a 0, and that's a 1. I think you can tell it's the opposite of this one. Interesting. I propose a theorem. I propose a theorem which we pretty much proved that A equal B is pretty much the negation of, is identically equal to negative of A exclusive OR B. That's famous theorem.
Dan's theorem.
Yeah, that's not my theorem. That's actually, I've seen it in books and stuff. So like, yeah, that's how it's so easily come up with. But yeah, and then we have, let's see, then following this we have the monotone laws. This was a little bit hard for me to understand, but why they separated it like this. But monotone law means that I'm not really sure what the relevance of this is, but that one of the arguments can change from like 1 to a 0 or something, or from let's see, changing anything from a 0 to a 1 never changes the result from 1 to 0. And I'm not sure what the significance of that is. It never invalidates an argument, I guess. Yeah, I guess maybe that's the importance of it. Changing something, these monotone laws, meaning that if you follow the monotone laws, then you never invalidate an argument by changing the result from 1 to a 0. I'm guessing that's what that significance is, why they separated the monotone laws. Does anybody know? Can anybody illuminate me on that?
Changing a 1 to a 0, but you can change 0 to a 1.
You can't. Yeah, it's just the monotone laws. These monotone laws mean that they're called monotone laws because none of those things in here. Here's the first monotone law, is the associative law, which means that the associative law for conjunction, or and, is is the same thing, identically equal to A and B and C, which is kind of self-evident, and as is the one for OR. I just substitute OR, blah blah blah.
Yeah, I recognize that. I I don't remember the name of the law, but I know it's a law.
Yeah.
I think it's distribution, law of distribution.
No, it's the law. It's not distribution. It's associative law.
Oh, that's right.
It's like saying in algebra A plus B plus C is identically equal to A plus B plus C, just like in algebra for addition and multiplication. So we'll get that out. But yeah, that's just like that. And here the associative laws. The associative laws have been stated. Commutative laws, same thing. Conjunction A and B is identically equal to B and A. Blah, blah, blah. Okay. And then there are distributive laws. Now, distributive laws are funny. In algebra, you have like multiplication is distributive over addition or something like this, what do you call, but not the other way around. But in Boolean algebra, in this algebra, turns out that not only is conjunction distributive over disjunction, but disjunction is also distributive over conjunction. That is, in algebra, you have A times B plus C is identically equal to AB plus AC. But try to do that another way around, it just doesn't work.
You're really saying the same thing.
You're really saying, you try that another way around with addition over multiplication, it doesn't quite work. But what the amazing thing about this algebra is that you have a new law. Basically, you have two distributive laws instead of just one. You have the distributivity of the conjunction over disjunction and disjunction over junction. So here, conjunction. Oh, oh. Yeah. And then you change the symbol to like B and or C, and it's identically equal to, guess what, A and B. This one is not as apparent. You might want to use truth tables to kind of verify, but this is an easy exercise actually. But using them truth tables makes it so nice. But then you go 4 A and C. Then the other one, of course, I'm just going to reverse the symbols. Everything else is the same. Have I reversed the symbols correctly? Yeah, okay. That's the same damn thing. Isn't math nice?
It could also be
Yeah. Anyway, you got here's an identity which you got to well, you have these operations. I call them operations. So if you have an operation, there's an identity to the operation. There's also the inverse, isn't there? Interesting. I'll investigate this shortly. Okay. This is anyway the thing that you can put, that you can conjunct with A to give back A is 1. In other words, if A is false and 1, then that answer is false. which is the same as A. If A is 1 and 1, that's 1. This is the same thing as A. So that's one identity right there. Here's another identity. A or 0. This is still dependent on A, which if you look at that in a minute, I think you can see it's a pretty simple one again to see, because it's only two possible things A can be, and then it falls out. And here's something called an annihilator. I don't know what this, something they call the annihilator. Maybe this is the
Schwarzenegger one.
this is the inverse. My idea of the inverse. I wonder what the or inverse of. I wonder. Question mark. 4 questions actually, beginning with. Unless, how much time do I have left?
A few minutes.
Okay. How much time? I might have to go over a little bit, but I don't know, maybe I'll cover this in a minute. We have an outstanding question of inverses. I'll treat that if I have time. But annihilator means that we have A and 0 is always going to be 0. Doesn't matter what A is. A or 1 is always going to be 1. Those are the two annihilator statements. Idempotence says that A and A is going to be the same value as A, same thing for or. And absorption, I'll just go ahead and write that out. A or A is identically equal to A. And something they call absorption, which kind of you'll kind of see why they call it absorption when I write it out here. A and A or B is identically equal to A. I might derive one of these. A or B and A and B is identically equal to A. I might use the distributive property, convert that A and A. And then I have or I'm working with this one, I'm proving it. And I'm saying the B and A or B, no, A and B, or A and B. So, see if I can prove this thing. A and A reduces to A. Or did I run myself into a corner? I don't know. A or A. Lost. Okay. I thought I'd take the exercise to see.
That's alright.
Sometimes the teacher gets stumped, you know.
Yeah.
All right, let's see.
We're all fallible.
Anyway, this is got. I get into non-monotone now. The thing that is any of these changes, whether the A changes, evidently the result does not change from a changing a 0 to, what did I say back here on the paper? Changing a 0 to, or true, yeah, changing A, B, or C from 0 to 1 never changes the result from 1 to 0, evidently, which is why they call them monotone laws. These are the non-monotone laws, and we'll run immediately up against one that does change, complementation or negation, double negation. Yeah, let's see. Yeah, here complementation. Okay, A. Oh yeah, this complementation is A. This thing we got A or and minus A. Usually they write that in parentheses, but I'm always doing the minus before I do that. Of course, I put that in parentheses just for sticklers. And it's A minus A, and that is always equal to 1. And double negation, which the old minus A, which I brought up earlier, is always going to be A. And then, De Morgan was another mid-19th century, and he worked on this thing called De Morgan laws, and here they are. I may be running out of time here, so I'll just write them down real quick. The conjunction of the negations is identically the same as the negation of the disjunction.
Makes sense.
Yeah, and here we have the negation, the disjunction of the negation disjunction of the negations is equal to the negation of the conjunction.
Yeah, I know when you're constructing complex truth tables, the Morgan's theorem is one of the most handy tools you can have.
Yeah. That's two De Morgan's laws.
I see why these two classes should have gone together.
They go perfectly together.
Yeah.
They're practically the same thing.
Yeah, it's great. I can just look over here and be like, oh yeah,
that's true. This is good. You're right.
That's pretty much it, unless you want me to figure out what the inverse of questions. Just as you have 7, minus 7 is the additive inverse in algebra of 7. Just as 1 over 7 is its reciprocal or multiplicative inverse. Now, pose the same question for 0 and 1. There are 4 questions, 0 or 0 or false. What, if any, this is an exercise, is the inverse, is the, we'll call it the conjunctive inverse I have not considered this beforehand. It came up of this number, of this quantity here, the 0, which we note is false. What is the conjunctive inverse of that? Another question, what is the disjunctive inverse? Same 2 questions.
They're the same.
For that guy, same questions. Let's tackle the 0. Okay, you remember that the identity, that the inverse means that you multiply the or that you operate on the original argument and you obtain the identity in that operation. If you multiply 7 times 1 over 7, you end up with the multiplicative identity, which defines the multiplicative inverse. Okay, then is there something you can conjunct with 0 to obtain the conjunctive identity would clearly, from our laws, be 1. The conjunctive identity is 1. The disjunctive identity is 0. So is there something we can conjunct with 0 to obtain the conjunctive identity of 1? I don't think so. Therefore, 0 does not have a conjunctive identity. Does not exist. Yeah.
Yeah.
Okay, so 0 doesn't exist. How about this disjunctive identity? If we multiply 0, the disjunctive identity of 0 is 0, because we can multiply, we can disjunct 0 with 0 and obtain the identity. So that's what the answer is.
So what's that?
Is 0. The disjunctive identity of 0 is 0.
But it still means
is itself. It's its own disjunctive identity. And so here's the same question now for 1. What is the conjunctive identity for 1? 1. Because 1 and 1 is a 1. So we have the answer there has an answer of 1. So now what is the disjunctive identity for 0?
Well, it could be anything.
I think it'd be 0.
Yeah.
Because that's the only thing that gives value, otherwise it'd be 1. Remember, we're looking for, as a result, we're looking for that, which gives us, interesting, one of these things doesn't exist, the other 3 do. I never knew that.
So 1 has disjunctive properties though?
Yeah, there is no conjunctive identity for 0.
For 0. But there is a disjunctive for 1.
There is
both
a
for 1.
Yeah.
for all other possibilities, all the other 3 questions I posed, there was an answer.
The only one that's exclusive.
The only one that didn't have an identity inverse. The only one that didn't have an inverse in conjunction.
I thought if you had a disjunction, only one had to be true.
Yeah. See, so I
Like if
just.
you had 0 or 1, and either one could be true.
So this
As long as the other was
is
false.
equivalent to 0. This is equivalent to 1. This is equivalent to 0. That gave. Now I'm checking my work here. That is 1. That is 0. Yep.
What about the disjunctive of 1 though? Like you have 1 and then and, is that and?
Yeah.
1 equals 1, but what about 1 or 1?
1 or 1 is still 1.
It's the same.
1 or 1. What your 1 or 1 is? You're trying to find disjunctive. Oh, I messed up here. And what I'm trying to do is they're trying to multiply by 1 or. Yeah, 1 or. What do I do? Or, oh yeah, I end up with another no answer. because
That's
there's
what I thought,
nothing.
since they haven't
I fucked up. Okay.
So surely there's only two.
This is not symmetric. Yeah, this is not. Yeah, this is indeed symmetric. I was wondering why the asymmetry. Why the asymmetry? Okay, I fucked up. Usually you're asymmetric in Boolean algebra. You fucked up somewhere else. All right. All right. This is there's nothing you can OR with one to give the OR identity. So this doesn't have an answer.
That makes sense.
That's what I thought.
That's what I was.
Okay. Yeah. All right. Yeah. Well, thank you for the exercise.
Thank you.
Thank you.
Hell yeah.
Complete understanding.
Yeah. That especially when I can do it. Especially when I do a fucking exercise. During my.